All right, I hear you've got a big test coming up, maybe even this Wednesday, and you need to get the absolute core concepts of climate science down, like, right now. Well, you came to the right place. Let's treat this as your ultimate last-minute study guide. Okay, let's just dive right in. We're going to go on a super fast tour of all the essentials you need to know. We'll start with the sun, the engine of the whole system, and go all the way to what the future of our energy might look like. Let's do this. So, first things first, we've got to start with the sun. You can think of it as the giant engine that drives our entire climate. And it all kicks off with one really simple, really important fact, that solar energy isn't spread out evenly. Okay, so this word right here, insolation, you're going to want to remember that for the test. It's just a way of saying how much solar energy hits a certain spot. And look at that difference. The equator gets blasted with 2.5 times more energy than the poles. This huge imbalance is basically the starting pistol that gets all of our planet's weather and ocean currents moving. And this is the simplest way to picture what happens. The best way to think about it? It's just like a pot of boiling water on the stove. The superheated air at the equator gets less dense and rises up. Then it travels, cools down, and sinks back to the surface. It's this constant loop, a convection current that's always trying to move that heat away from the equator. And all this action, all our weather, it's happening right here in the troposphere, the lowest layer of our atmosphere. Now, here's a cool little fact for you. See that boundary just above it, the tropopause? It's so stable and calm that commercial jets use it like a superhighway in the sky to stay out of all that turbulence. All right, so we've got that basic engine down. Now let's zoom out and see how that simple convection idea creates these absolutely massive planet-wide systems. These are basically Earth's air conditioners, just constantly moving heat around the globe. So you'd think it would be pretty simple, right? Hot air rises at the equator, travels to the poles, cools and sinks, one giant loop in each hemisphere. But that's not what happens. The planet's own spin throws a pretty big wrench in the works. Okay, this one is super important for your test, the Coriolis effect. You gotta know this. Because the Earth is spinning, anything moving long distances across its surface, like air, gets pushed sideways. In the northern hemisphere, it curves to the right. In the southern hemisphere, it curves to the left. And that powerful force is what shatters that simple single loop of air. And this is what you get as a result. That Coriolis spin is so strong, it actually breaks that one big loop into 3 smaller, interlocking cells in each hemisphere. You get the Hadley, Ferrel, and Polar cells. They all work together like these giant gears in the planet's atmospheric machine. Now, right where those 2 huge Hadley cells, one from the north, one from the south, smash together at the equator, you get this thing called the ITCZ. All that rising air means tons of moisture, which means lots of clouds and rain. Just think of it as the planet's main rain belt, and it actually moves north and south as the seasons change. Okay, another big one you need to know is the El Niño Southern Oscillation, or ENSO. It basically flips back and forth between these 2 phases. In an El Niño year, the normal trade winds actually reverse, and they push warm surface water over towards South America. But in a La Niña year, those same winds get super strong, pulling up even more cold water from the deep. These changes can have a huge impact on weather all over the globe. Okay, so we've got a handle on the basic machinery of the climate. But how in the world do scientists take all that and build models to predict what's coming next? So they use these incredibly powerful computer simulations. The easiest way to think about it is they basically divide the entire planet, the oceans, the atmosphere, everything, into a giant 3D grid, like a bunch of boxes. Then they add time as the 4th dimension. And for every single one of those boxes, at every single step in time, they solve the fundamental equations of physics and pass the results on to the next box. But wait, how can we actually trust these super complicated models? Well, this is where it gets really clever. We test them against the past. It's a process called hindcasting. Basically, scientists feed the models data from the past, like old solar activity or big volcanic eruptions, and see if the model can accurately recreate the climate that we already know happened. If it can predict the past correctly, we can be a lot more confident about its predictions for the future. All right, let's shift gears a bit, because the models can give us a picture of the future. But knowing the science is only half the battle, right? Acting on it is a totally different thing. So what actually gets people to change their behavior? This stuff is so interesting. When researchers looked into this, they found it really boils down to these 4 things. People are most likely to act when they believe, 1, I can actually do this, that's self-efficacy. 2, what I'm doing will actually work, that's outcome efficacy. 3, when they feel bad, like guilty if they don't act. And 4, when they see that, hey, everybody else is doing it too. Okay, let's wrap up this whole study session with a really powerful idea about the future, one that might actually surprise you. And it's not driven by policy, it's all about pure economics. Check this out. This quote is from a major study just last year, and it suggests something huge might have already happened. We may have already passed an economic tipping point where solar power is just destined to take over the world's energy markets. Not because of new laws, but simply because it's becoming the cheapest option. Period. So what's the engine behind this massive shift? It's this number right here, -15%. That was the average drop in the price of solar panels every single year between 2010 and 2020. That relentless cost reduction is the economic force that's making solar's rise feel almost inevitable. And you can see what that looks like in their projections. When the researchers ran thousands of simulations based on these trends, almost 3/4 of them ended with solar providing more than half of all of our electricity by 2050. That suggests solar dominance isn't just a wild idea, it's actually the most likely future. Which leaves us with a final big picture idea to think about for your test and just in general. If cheap solar is pretty much inevitable, then the whole conversation changes. The big questions aren't if we should transition anymore, but how we manage it. We need to start focusing on the next set of problems like keeping our grids stable, making sure everyone has access to financing, and managing the supply chains for all this new tech. All right, that's your crash course. Good luck on the test. You've got this.